Hello. Well, I'd like to talk a little bit more about twinning, and more to explain the geometry a little bit, because there are some important things to note when it comes to recognizing an FCC, a twinning an FCC material. So we'll start with our FCC lattice, as you see here. My twin plane is the one that's parallel with the desktop here, and there's another. When we look down the 110 direction, there's another twin plane here. And these planes are 71 degrees from one another, roughly. And that's important because then that you have to recognize when you're seeing these planes in a diffraction pattern, what the zone axis is that's corresponding with these planes. So what I've done here is put a series of crosses on some of the atoms so that you can recognize them. So when I do the twinning operation, and if you remember, the twinning operation involved a shear of a partial dislocation of the 112 type partial dislocation, perpendicular to the 110 direction and parallel with the plane of the twin. So we do that shear, 1, 2, 3, 4, 5. And what we've done is we've changed the orientation of the crystal. So notice now that the 111 plane here, which is undistorted by that twinning operation, is now at a different angle. So if I go back to, we see that the 111 plane is here, do the twin, the 111 plane is here. It's rotated from this angle to this angle. And the angle between the starting plane and the finishing plane, I mean, you could call this the second undistorted plane, but in fact all of the planes in an FCC are undistorted after the twinning operation. And undistorted, by undistorted I mean like you still retain the characteristics of the plane. It's not twisted or deformed in any way. So this 111 plane, as you can see from the crosses, when you do the twinning operation, the crosses are all nicely aligned when it comes to the orientation relative to the plane itself. So, so we have this shear of the 111 plane going from this direction to this direction, and that's roughly 38 degrees. Well, 38 degrees, roughly, approximately. So the reason I mention that is because I've seen cases in the literature where people talk about recognizing twins from the orientation of the 111 planes and making the point that you look for a 60-degree angle. Well, there is no 60-degree angle involved in the twinning shear. And what they probably mean when they talk about that is the angle between the bonds here in the basal plane. So these are all 60 degrees, 1, 2, 3, 4, 5, 6. And that's probably then gets confused with the characteristic angle of the twinning direction, which is 38 degrees, and the characteristic starting angle of the two 111 planes that characterize the 110 zone axis is 71 degrees. So there's no 60 degrees involved. Now the important thing about twinning, as I said, is that there's no all of the planes are essentially undistorted after the shear, which is good, because then you don't have to worry about what you do in other crystals is the requirement for a shuffle. So the twinning in other crystals often or many of the twinning operations, not all, but many of the twinning operations, especially for hexagonal close pack materials. In hexagonal close pack materials, any twinning operation involves a shear and then a shuffle. So you shear and you have one undistorted plane, and I've talked about this in the videos, for example, the basal plane. And when you rotate the basal plane, the rest of the crystal has to conform then to that reorientation of the basal plane. Just to recap, I mentioned it previously, when it comes to the FCC crystal and the hexagonal close pack crystal, there's another shear operation that can occur, and that is a martensite shear, which is every second plane, and that changes the crystal from a FCC to a HCP crystal. So this is the corrugated 1/10 plane in the FCC, in the ACP. So we'll go back to the FCC now. So you can transform with that martensitic shear back and forward between the hexagonal close packed and the FCC structure, face-centered cubic structure. There was one other thing I wanted to mention. Oh yeah, so one of the other things I've seen described in literature is people would say a certain amount of shear of things like cavities and say, oh, well, you know, that shear is massive, like this, it's much more than the 38-degree tilt that I'm talking about here. But what is being missed often is that you can do, if I start from this direction, you can perform one twinning operation. But if you want, you can continue and do another twinning operation. Slightly different angle, slightly different 112 direction. And that second twinning operation, and actually multiple twinning operations from that point on, that brings you back into perfect register, and you would not see any stacking fault at the twin boundary once you've done two twins. So even numbers of twinning operations brings the crystal back into coherency. So you don't see a twin. What you see is basically the bulk shear. And there's nothing stopping you twinning again. Whoops, except being able to hold onto all the balls. Anyway, so in an unconstrained system, you can get multiple shears. So the concept that twinning is only a limited amount of shear is not true. You can have multiple shearing operations, and therefore as much of a shear of defects like cavities, voids, as you want. And again, this is another issue that appears in the literature, and people have to recognize that that is not the fact that you see a massive amount of shearing does not mean that it's not because of a twinning operation.